Hello. In this video, I will talk a little bit about redox reactions, that is oxidation reduction reactions, particularly how they are dealt with by organic chemists. But before we do that, we really need to understand oxidation numbers and how we assign oxidation numbers to particular atoms in a molecule. This is kind of an algorithm where there's a series of rules you have to learn in order to assign oxidation numbers. First, and this is what we call a hierarchy, meaning that the first rule we will learn is always true, the second rule is true unless it conflicts with the first rule, and so on. So the first and most important rule says that the oxidation numbers of all atoms in a molecule or ion must add up to the overall charge. So as examples, I've listed methanol, CH3OH. What this rule says is that once you've assigned oxidation numbers to the carbon, these three hydrogens, the oxygen, and that hydrogen, all the oxidation numbers have to add up to zero because the overall charge on the molecule is zero. It's not an ion, it's a neutral molecule. Whereas in ammonium ion, the oxidation numbers, once they've been assigned, for the nitrogen and the four hydrogens, all have to add up to a total of +1 because the overall charge on that molecule is +1. Second rule, and this one is always also true, the oxidation number of any atom in the element state is zero. In other words, if you want to assign the oxidation number of oxygen in the molecule O2, it's going to be zero because this is the element, oxygen. It's not combined with any other atoms. Similarly, in iron, that's iron metal, not the ion iron, but iron metal, its oxidation number is zero. And notice that H2, the oxidation number is zero because that's the element hydrogen. Now if that's H2O, it's not because that's not the element hydrogen. But if it's in the element state, the oxidation number is always zero. Third rule, the oxidation number of a simple ion is always the same as its charge. And this kind of goes along with the first rule, that since the overall charge is -2, the oxidation number of the oxygen must be -2. And in a magnesium +2 ion, the oxidation number is a +2. And in this ion, which is H-, that's a hydride ion. It's not one we see very often, but it's an important one. H-, the oxidation number is -1 because the charge on the simple ion is -1. That's a pretty easy rule. Fourth rule, and this is where we start getting into specifics. We're going to talk specifically about hydrogen in this case. Hydrogen will always have a +1 oxidation number unless one of the previous rules says otherwise. So in the molecule H2, as we saw, the oxidation number of the hydrogen is at 0 because it's the element hydrogen. That rule takes precedence over this one that says it's always a +1. Or in sodium hydride, in which you have a negative charge on the hydrogen, so it's a hydride, H-, the oxidation number is -1, as we saw a minute ago, but that's because the previous rule breaks this one that says it's a +1. Other than that, any hydrogen will always be a +1. So in methane, CH4, oxidation number of hydrogens is +1. H2O, oxidation number of +1. Any other compound of hydrogen with other stuff, unless it's H-, it's going to be a +1 oxidation state. So just basically hydrogen's always +1 with a few exceptions. Rule number 5, oxygen. This is the oxygen rule, and it says that it will always have an oxidation number of -2 unless one of the previous rules says otherwise. So one of the previous rules says the element oxygen is the oxygen is always at 0, so that's breaking this rule. Look at this interesting molecule, H2O2. Since the previous rule says hydrogen is always a +1, and since the overall charge has to add up to 0 because this is a neutral molecule, if we have two +1s for the hydrogens, then the two oxygens must each be a -1, and so the oxidation number of oxygen in this molecule, H2O2, is -1. That breaks the oxygen rule that says it's always a -2, but that's because previous rules say otherwise. Other than that, oxygen is always a -2. So in water, H2O, oxidation number of oxygen is -2. Sulfuric acid, oxidation number of oxygen is -2, and so on. And now this one, notice that there are 4 oxygens. Each of those oxygens has a -2 oxidation number. The next rule says that, again, unless the previous rule applies, all halogen atoms will have an oxidation number of -1. But again, it has to, other rules may apply earlier. So for example, Br2, the element bromine, again, because it's an element, its oxidation number is going to be 0. Look at this interesting molecule, HClO3, that's chloric acid. What's the oxidation number of the chlorine here? Well, it turns out to be a +5. Again, that breaks the rule that says it's always a -1, but that's because the hydrogen has to be a +1, as the previous rule said. The oxygens each have to be a -2, as previous rules said, and therefore the chlorine must be a +5 to make the overall come out to be 0. Since we know this is a neutral molecule, has no charge, the oxidation numbers all have to add up to 0. And since we have 3 -2s, that's a -6, and 1 +1, then the chlorine must be a +5 to balance it out. But again, that breaks this rule, but typically this rule is going to be true. That should be CCl4, carbon tetrachloride. The oxidation number of the chlorine is -1 because chlorine is always -1 unless previous rules disagree, but they don't in this case. And similarly, the bromine here is a -1 because bromine is always a -1 unless previous rules disagree. Rule number 7. The oxidation number of any other atom must be determined by the previous rules. So here's a question. What are the oxidation numbers of all of the elements in methanol, CH3OH? Hydrogen is what? Always +1. So that's rule number 4. Hydrogen's always +1. What about the oxygen? Oxygen's always a -2. And that's rule number 5, which says oxygen is always a -2. So therefore, what must the carbon be to make the whole thing come out to be 0? Carbon must be a -2. So notice -2, +1, +1, +1, -2, +1. They all add up to 0. Another example, what are the oxidation numbers of all the elements in this molecule? Well, there's a hydrogen rule that says it's +1. There's an oxygen rule that says it's -2. There's a chlorine or halogen rule that says it's -1. And therefore the carbon must come out to be -2. Here are some more molecules for you to work on. And I would pause the video at this point and just try to assign oxidation numbers to these particular molecules. And notice trends as we go from a triple bond to a double bond to a single bond, what happens to the oxidation number of the carbon. And as we go from methane to methanol to formaldehyde to formic acid to carbonic acid and carbon dioxide, what happens to the oxidation number of the carbon. Now, what about molecules with more than one different carbon? This is where it gets a little bit more complicated for organic chemistry. So for example, if we're going to assign oxidation numbers to all the atoms in this molecule, how do we handle it since we have a bunch of different kinds of hydrogens and a bunch of different kinds of carbons and an oxygen? How do we assign oxidation numbers? Well, basically what we're going to do is we're going to break up the molecule into individual carbon pieces. So this whole CH2OH group we're going to break off and just treat it as HOCH2 as if that were a separate molecule. And then the CH2 we're going to treat as a separate molecule, and then the CH we're going to treat as a separate molecule, and CH2 we're going to treat as a separate molecule. In other words, basically just in your imagination, make all the bonds between the carbons disappear and treat them as separate molecules. So notice then that the HOCH2, this carbon, must be a -1 because the oxygen is a -2. Each of the 3 hydrogens is a +1, so therefore the carbon must be a -1. And in this case, since each of the hydrogens is +1, the carbon must be a -2. And in this case, since the hydrogens are +1, the carbon must be a -1. And in this case, since the hydrogens are each +1, the carbon must be a -2. So notice the oxidation numbers. In this case, the carbon's a -1. In this case, it's a -2. In this case, it's a -1. And in this case, it's a -2. So different carbons in the same molecule can have different oxidation numbers. Now for practice, again, I would suggest pausing the video and see if you can assign oxidation numbers to these 2 molecules. Again, divide each of the carbons into a separate molecule. So you'll have a CH3, a CH, a C with nothing else on it, a C with just a double bond O on it, a CH2OH, and a separate CH3 down here. And in this case, of course, you'll have a CH3. You can figure that out separately. A CH2, you can figure that out separately. And then treat each of these carbons separately and see what you come up with for oxidation numbers on those. And don't forget that some of these carbons may have other hydrogens on them as well, because in the polygon type figures, the hydrogens aren't shown. And that's the end of part 1.